4,500 years ago, before the wheel was common in Egypt, before iron tools, before cranes, before anything we'd call machinery, a civilization moved over 6 million tons of stone and stacked it into a mountain so precise that its base is level to within just a couple of centimeters. The Great Pyramid of Giza contains an estimated 2.3 million blocks. Some weigh as much as a city bus, and it was built in roughly 20 years. So how did they do it? No steel, no engines, no pulleys as we know them. Today, we're breaking down exactly how the ancient Egyptians pulled off one of the greatest engineering feats in human history, and busting a few myths along the way. Let's kill the aliens myth right away, because it undersells actual human beings. For decades, popular culture pushed the idea that slaves, or worse, extraterrestrials, built the pyramids. But archaeological digs starting in the 1990s uncovered entire worker villages near Giza, bakeries, breweries, medical facilities where broken bones had been set and healed, cemeteries where workers were buried with the same honor as respected citizens, close to the pyramids they built. These were skilled laborers, many of them farmers who worked during the Nile's flood season, when their fields were underwater and useless for agriculture anyway. It was organized, paid, seasonal labor on a massive state project, closer to a national infrastructure program than a slave camp. Estimates suggest around 20 to 30,000 workers at any given time, rotating in shifts. Feeding that workforce required its own logistics miracle. Bread, beer, and meat delivered daily, which is a whole engineering story in itself. Most of the pyramid's core blocks are limestone, cut right from quarries near the construction site. The outer casing stones, the smooth white shell that would have made the pyramid gleam in sunlight, came from Tura across the Nile and were finer, more polished limestone. For cutting, workers used copper chisels and saws along with harder dolerite hammerstones to pound softer limestone into shape. Copper is soft compared to the stone it's cutting, so workers relied on abrasive sand as a cutting agent, dragging copper saws through wet sand to slowly grind through rock, the same principle as sandpaper. For granite used in the king's chamber and weighing up to 80 tons per block, the process was tougher. Workers used dolerite pounders, some of the hardest stone available to them, essentially hammering the granite into shape through repeated percussion, block by block, for months. One clever technique. For extracting large blocks, workers would carve grooves into the rock face and hammer in wooden wedges, then soak them with water. The wood expanded as it absorbed moisture, and the force cracked the stone along a controlled line. It's slow, it's precise, and it works. This is the part that baffles people most. How do you move a 2.5-ton block, let alone an 80-ton granite one, without trucks? The answer, largely, is sledges and sand, and a discovery that made headlines in 2014. A team of physicists from the University of Amsterdam studied a wall painting from the tomb of Jehuti-Hotep, showing workers dragging a giant statue on a sledge. One figure stands at the front of the sledge, pouring water onto the sand. For a long time, people assumed this was ceremonial. Turns out, it's physics. When you wet sand to the right consistency, it stiffens and reduces friction against the sledge by roughly half. Too dry, and the sand piles up in front of the sledge, creating resistance. Too wet, and it turns to mud. But at the right moisture level, the sand grains bond together just enough to let the sledge glide smoothly on top. That single trick could have cut the labor force needed to move heavy stones by half, meaning fewer workers could move the same load, or the same number of workers could move it much faster. For the largest stones, evidence suggests Egyptians also built and maintained hard-packed, leveled roads out of clay, limestone chips, and gypsum, functioning almost like ancient highways specifically for hauling. Here's where Egyptologists still argue. Once you've got the stone to the site, how do you get it up the side of a structure that eventually reaches 481 feet tall? There are three leading theories. The straight ramp theory suggests a single long ramp built directly against one face of the pyramid, growing taller as the pyramid did. Problem. For the Great Pyramid's height, this ramp would need to be over a mile long and would require more material than the pyramid itself. The spiral ramp theory proposes a ramp wrapping around the exterior of the pyramid, rising as it circles. This uses less material but makes it nearly impossible to keep the corners perfectly aligned, since the ramp would cover the very corners surveyors needed to check. The internal ramp theory, gaining real traction after a 2018 discovery inside the Great Pyramid itself, suggests a spiral ramp built into the pyramid's body, tucked just inside the outer casing. Most researchers now believe it was likely some combination. External ramps for the lower levels, transitioning to internal or corner ramps higher up, where hauling massive stone up a mile-long external slope would have been impractical. Whichever method, the workers used levers made of wood to nudge blocks into their final position. Small, incremental adjustments done by hand with obsessive precision. Here's the detail that really should blow your mind. The base of the Great Pyramid is level to within about 2 centimeters across a footprint of over 13 acres. The four sides are oriented to true north with an accuracy of within a fraction of a degree. How without lasers or satellites? For leveling, most Egyptologists point to a simple method. Workers likely dug a grid of trenches around the building site, filled them with water, and used the water's naturally flat surface as a reference line, then carved the surrounding bedrock down to match that level. Water doesn't lie. It's the most reliable level you can find in the ancient world. For alignment to true north, the leading theory involves the stars. Egyptian astronomers likely tracked 2 circumpolar stars, stars that never dipped below the horizon, as they rotated around the celestial pole, and bisected the angle between their positions to find true north. It's not guesswork, it's applied astronomy done with ropes, stakes, and centuries of accumulated observation passed down through generations of priests and architects. In 2013, archaeologists found something extraordinary at Wadi el-Jarf on the Red Sea coast, the oldest inscribed papyrus ever discovered, a logbook written by a middle-ranking official named Merir. His diary describes his crew's job, hauling limestone blocks by boat from Tura to Giza, trip after trip, logged with dates and quotas like a modern shipping manifest. It's proof that the pyramids weren't built through brute force alone. They were the product of a functioning bureaucracy. Supply chains, payroll, scheduling, quality control. In many ways, building the Great Pyramid required Egypt to invent large-scale project management, 4,500 years before the term existed. No aliens, no lost technology. Just tens of thousands of skilled, paid workers, brilliant low-tech engineering, obsessive precision, and a level of organization that rivals anything we'd call modern. The pyramids aren't a mystery because we lack an answer. They're a mystery because the answer is almost harder to believe than magic would be. If you enjoyed this, subscribe for more deep dives into ancient engineering, and let me know in the comments which ancient mystery you want covered next.